Okay, so good morning to all of you. So we will start a new lecture today, lecture number 27, in which we will discuss the structure of crystalline solids, and we will begin with among this category of materials with glasses. Okay, so what we have, so let me just give you a recap of previous two lectures. So in the previous few lectures, we discussed about structures of ionically bonded solids, which are also basically ceramics, and most of them many of them turn out to be oxides, but there are other materials like carbides, fluorides, halides, and so on and so forth. So in this we saw that these structures are based on assembling of cations and anions, and by the virtue of minimization of potential energy, they tend to make crystal structures in which cations and anions are arranged in an ordered fashion. So what happens is that since anions are bigger, anions typically form the base lattice. So they form the basic skeleton of the material. For example, it could be FCC based structure, it could be HCP based structure, or it could be non-FCC but cubic, or it could be non-cubic as well. So among these three categories, where anions basically form a base lattice, they pack themselves in face centered cubic lattice form or hexagonal closed packed lattice form. The cations go and occupy the interstices, which are typically octahedral and tetrahedral, but they could be some other kind of interstices as well, which they occupy depending upon their radius ratio. So we discussed that radius ratio determines by and large to which interstices the cations will go, and as a result you form various structures. So we looked at variety of materials, such as in cubic category we looked at sodium chloride, zinc sulfide or zinc blend structures, calcium fluoride based structures, and spinel structures, which are basically Ab2O4 kind of structures. And then we looked at some other structures such as perovskite, we looked at CSCl, and so on and so forth. And then we looked at some non-cubic structures such as YbCO, LSCO. These compounds make tetragonal orthorhombic unit cell, and within this unit cell there are perovskite units or sodium chloride units. And then we finally looked at HCP structures, starting with the zinc sulfide based woodsite structure, and then we looked at corundum based structures, and then derivative of corundum such as ilmenite, Li lithium niobate, and so on and so forth. And then we looked at what was the rutile structure. So these were the very common structures that you come across in ionic solids. Now, however, there are some oxides which are also which have a large fraction of covalent bonding, and they tend to crystallize in a non-crystalline form. So in this lecture we will start with materials which are non-crystalline materials, which do not have a periodic structure over long range. They may have periodicity over short range, short range. By short range we will mean maybe a few nanometers. There is a very fuzzy definition about short range, but typically of the order of a few nanometers. So they may have periodicity over short ranges, but no periodicity over long distances. When you for example look at few tens and hundreds of nanometers, the periodicity breaks down. So, they may have periodicity over short range, but they do not have periodicity over long range. Such structures are typically open structures, and they have varying bond lengths. So, as a result, since they have varying bond lengths, so if you look at the energy minimum, it goes something like this. So, you have, right. So, this is potential energy, this is distance. If a material has varying bond lengths, what it means is that it also, it also means that you will have varying bond energies. And if you have varying bond energies, it also means that you have a range of temperatures at which melting occurs. So, that is where they have very diffused melting phenomena. And this is basically characterized by the materials having typically a glass-like behavior, and as a result they have something called as TG, which is called as glass transition temperature. So, I will not get into details of what the physics and the thermodynamics and kinetics of glass formation, but basically these materials do not crystallize themselves in a crystalline form. As a result, they tend to form structures which are non-periodic glassy structures. So, there are materials such as, so I will show you some slides on just if you look at, for instance, this slide. So, this, for example, this is taken from Wikipedia. So, this is a natural glass which is formed by a meteorite impact. This is called as Molda white. So, you can see that it has this nice greenish texture and sort of transparency in its flakes. So, it has this naturally solidified structure which is basically a glassy structure. Then this is another glass which is called as trinitite, which is a glass made by the Trinity nuclear weapon test. So, again it has undergone solidification. Solidification does not result in formation of a periodic structure. Similarly, and there are plenty of applications of these glasses. For example, when you add the impurities to these glasses, these impurities tend to give it different colors. So, you can see that these different colors of glasses, all of them are transparent, but they have different colors. Again, you can see on the left you have different colors of, you can see the greenish texture. You can see the advantage of glass is that since glass is glass melts at lower temperature, it has a broad range of melting temperatures. As a result, it can be blown into, it can be casted and blown into various shapes. So, this is for example, a complicated shape out of glass. It can be transparent as well as opaque depending upon how you make it and what is inside it. So, glass is a very important and very fascinating material, and its solidification phenomena of glass is something which is which is not yet very well understood. The physics of that is still perplexing. So, you can see that this is a transparent window glass, this is a painting on which you have a glass cover, this is a Roman cage cup which is from 4th century AD. So, you can see that 4th century on as old as 4th century you had glasses. So, glass is something which has been in existence since long time. Humans have been using it in a variety of applications. However, it is something which is not as well as understood as metals are in comparison to crystalline materials. Variety of these glasses happen to be non-crystalline silica. So, glasses are used in a variety of applications. They are used for fabricating things like vessels and windows, as we see on daily basis, potteries and so on and so forth. Most of the time the basic component of this glass happens to be silica. Silica is basically SiO2. So, SiO2 happens to be the basic building block of these glasses, and this amorphous phase basically which we have at room temperature, it crystallizes upon solidification. It solidifies as if all of us know that liquid has a random structure. It is as if the liquid has frozen in the same structure upon solidification. We add lot of impurities to glass, for example, sodium oxide and all that to lower the viscosity, and various like boron oxide, sodium oxide, all these impurities are added, potassium oxide, these are all added to glass to make it to change or to modify its viscosity and to make it softer or harder, and these impurities also change the glass transition temperature, the temperature at which glass will soften or glass will melt. So, they have several, you can tune the glasses very well. As I said that the essential issue in the glasses is that there are bonds of different lengths, and this different length bonds, as I told you in the previous slide, the different lengths of these bonds. If you have, for example, this is a potential energy plot, okay. So, this is E versus R. If you have bonds of different lengths, okay. So, let us say R1, R2, R3, R4, R5. In case of crystalline material, you have a minima at R0, okay, and that is what you have all over the place. In case of glasses, what happens is that since you have this multitude of bond lengths, which means you have an energy corresponding to R1 is E1, energy corresponding to R2 is E2, to this it is E3, to this again it is E4, and this again is E5. So, you have this multitude of energies, and these multitude of energies will mean you have multiple, in some sense it is like having multiple melting points, and that is why many a times glasses tend to have a diffused behavior, and that is why the solidification takes place over a range of temperatures rather than at a single temperature. And this is what makes glasses having a temperature called as glass transition temperature, which is called as Tg. There are 2-3 temperatures which are in which typically are talked in the context of glasses. We will not get into that. There is a concept of free volume and so on and so forth. So, we will probably skip that, but I just wanted to emphasize that this is the reason that you have variety of bond lengths, and there is variety of bond lengths force the material to have multiple solidify over a range of temperatures. So, let me now get back to notes. So, basically the basic building block in a glass is in a variety of glasses, not all of them, but in most variety of glasses is SiO2, which is called as silica, and by and large the structure of silica is such that silica has nearly 50% ionic bond and 50% of covalent bond. So, it has this character that it must have this kind of behavior. Now, if you measure if you take the radius ratio of silicon 4 plus to oxygen 2 minus, the radius ratio works out to be nearly 0.29, and this 0.29 you can see falls between 0.225 to 0.414. As a result, it must have a tetrahedral it is preferred to have a tetrahedral coordination. So, basically what you are going to have is you are going to have this atom of silicon which is 4 plus, okay, and this is surrounded by so we are going to have one oxygen here, another oxygen here, oxygen here, another oxygen here. So, this is O2 minus, O2 minus, 2 minus and O2 minus. Now, if you look at the sum of charges, silicon has 4 plus and oxygen has 2 minus into 4, right. So, the tetrahedra itself will have a charge which is minus of 4. So, if you now make this as a unit, this unit will have 4 minus charge, which means this needs to, so that tetrahedra cannot survive on its own, it has to connect with other tetrahedras or something else to neutralize the charge, so that it becomes charge neutral thing. The way it happens is that, so basically you can say it's electrically unbalanced, all right. So I can say that, so minus charge requires, there is electrical imbalance, and this requires sharing of polyhedra. Now, how does this sharing of, which means oxygen, whatever oxygen is there, it has to be shared between the polyhedra. So, how does this work? And this is the tetrahedra where, so you can say that this tetrahedra you can characterize at SiO4 4 minus tetrahedra. So, basically if you look at the structure would be, so if I just make a tetrahedra, right, this is the tetrahedra you will have, okay, and in between that tetrahedra you will have, sorry, this would be like this, and then you will have one here. So, in between of this tetrahedra you will have, so this will make a bond here, bond here, bond here. At the center you will have a silicon ion. Now, the way tetrahedras can share, polyhedra can share, is it can happen by corner sharing, it can happen by face sharing. In fact, after corner sharing it would be edge sharing, because what will govern the edge sharing, corner sharing or face sharing? Depending upon the way it shares, the distance between the cations will change. So, for example, if you look at the face sharing tetrahedra, you have a tetrahedra, let us say like this, all right, and if you make another tetrahedra sit on top of this, this is going to be the face which is shared. So, this one silicon atom is sitting here, another silicon atom is going to sit somewhere here. So, this is the distance between the silicon atom, SI distance, this is phase sharing. So, if I draw it like this, so how is it going to turn out to be something like that. So, you have a tetrahedra coming from the side sharing the face. So, this is going to be RSI as compared to what you will have when you have, for example, edge sharing. So, if you have edge sharing, this is your silicon atom, let us say this is your silicon atom, these are your oxygen atoms, okay. So, two are going to be present, one is going to be present somewhere here, one is going to be present somewhere here. So, you are going to have tetrahedra like that, and this another tetrahedra is going to be present somewhere like that only. So, this is another silicon atom, and other two oxygen atoms are going to be somewhere here and here. So, this is for example the tetrahedra, right. Okay. This is the edge sharing. So, this is the shared thing, and in this case this is the shared face, this is the shared face, this is the shared edge. So, you can see that this again there is a distance between these two atoms. So, R silicon silicon, this is let us say face, this is let us say edge. And then third configuration that is going to be possible is you have silicon atom, you are going to have one oxygen atom which is common to both of them, and other atoms are going to be present at certain, so it is not very accurate, but one bond, okay. So, this distance is now again R silicon silicon, and this is again oxygen. this is your corner sharing. Okay. So, this is going to give you again R silicon silicon C. So, as you can see that R silicon silicon in case of phase sharing is going to be smaller than cationic. So, now this has repercussions in terms of cationic repulsion. You can see that in case of phase shared polyhedra, there is going to be stronger cationic repulsion as opposed to in the case of corner and edge sharing. So, by and large, to minimize the cationic repulsion, so separation needs to be large. As a result, corner or edge sharing is preferred over phase sharing of polyhedra. So, as it happens in case of SiO4, the silicate tetrahedra corner sharing is preferred, okay, but it is not guaranteed that this is going to happen, all right. So, what you have here is, so let us first look at the however silica does make crystalline structure. So, let us first look at the crystalline silica structure and then we look at the other forms of silica structures. So, the first thing is if you cool it slowly enough and if you achieve right conditions, it will make a structure which is, so what you have here is silicon tetrahedron like that. So, let us say this is the tetrahedron top view, okay. The second tetrahedron is attached to it in such a fashion. This is the second tetrahedron, and the third tetrahedron is present in such a fashion, and the fourth one again okay, and this one is going to be shared with the guy right here, and then you are going to have one here, and this one will be other way around, okay, like this. So, basically this is how it is going to continue. And if you continue this in the 3D, you will form a silicate network, okay. So, this is the form of these are the hexagonal sheets of silica molecules arranged in a crystalline form. This is a periodic pattern of hexagonal layers that they form. So, this is the first structure crystalline form they make. If you break these the corners here or here or here or here, change the bonds, and if you manage to manage this to happen in a random fashion, then what you will make will be a amorphous form of silica. So, we will break here, we will look at the remaining forms of crystalline solids in the next lecture.